In this video, we would like to derive the volume of a cone using cylindrical coordinates. We could start from basic principles by writing the volume element in cylindrical coordinates, which is r, dr, dz, dphi, and then do the triple integral to get the volume of the cone, but we'll do it in a simpler way in this video. So on the right here we have a cone. The base of the cone is a circle that has a radius of a, and the height of the cone is h. If we were to take a thin slice perpendicular to the axis of the cone, we end up with a disk. That disk has a thickness that we will call dz and has a radius that we will call r. Now, depending on where you make the slice during the cone, if you make the slice at the top here, the radius is 0. If you make the slice at the bottom, the radius will be equal to a. So the radius of our disk depends on the height. So we need to find the relationship between the height at which we are taking the slice and the radius of the corresponding disk. So if we have our cone, let's draw our cone here. So if we cut our cone through the middle using a plane, then we'll end up with a big triangle. And let's draw this again. And this would be the axis of the cone. The line in the middle here would be the axis of the cone. So you'd like to focus on this triangle here. I'll just draw it outside. So this side here represents the axis of the cone, and it has a height of h. And the point from here, this would be the middle of the cone to the edge at the base. So this distance here is just the radius of the base, which we called a. And let's look at the disk here that has a height that we will call z. So this disk here, the height above the xy plane is z. So that would be here. So this height here is z. And the point from here to here, that represents the radius of our disk, r. So we want to find the relation between r and z. So this is a right angle triangle here. And then inside here we have a smaller right angle triangle. So this is a right angle. And let's call this angle alpha. So let's start with the big triangle. So the big triangle, if you write tan alpha, that equals tan of this angle equals the opposite side divided by the adjacent side. The adjacent has a height of h. Now, if you look at the small triangle here, tan of this angle equals the opposite side, which is equal to the radius of our disk element. And the adjacent here is actually the height of that disk element. So that equals to 0. So using these two, we have our relation between r and z. So let's write that here. So r equals a over a divided by h multiplied by z. And let's just plug in some values to see if that makes sense or not. So when z equals to 0, r equals 0. So that represents this point here. When the height above the... So actually I think I should have drawn this cone to be upside down, just to be consistent. So here's our cone. Let's draw it again. So this is x, y, z, and our cone is actually upside down. So when z equals 0, the radius of our disk element would be equal to 0. When z equals to h, r equals to a, which is at the top here. So this height here, when the element has a height of equal to h, the radius of the disk of this disk here is equal to A, which is the, we said that's the radius of the base of the cone. So now let's get back to our disk. So we have a disk, has a radius of R, and has a thickness that we've called dz. So what's the volume of this disk element? So dv equals, so we'll treat this as if it's just a very small cylinder. So we'll treat this disk element as if it's a cylinder. The volume of the cylinder is the area of the base, which is pi r squared. It's just a circle, multiplied by its thickness, which is dz. So now we need to plug in the relation between, let's call this 1, let's call this equation 1, and let's call this equation 2. So let's plug in 1 in 2. So we'll replace r with z. So dv equals pi r squared. We're going to replace every r by a over h times z. That's all squared times dz. That equals 2 pi a squared divided by h squared z squared dz. And to find the volume of the cone, we just need to do a single integral. So v equals the integral of dv, which is the integral of pi a squared h squared z squared dz. And we're integrating over z, so z changes from 0, z equals to 0, all the way until z equals h, which is the height of the cone. So the limits of the integral are from 0 to h. That equals pi a squared divided by h squared. All of these are constants, so we can take out of the integral. So it's pi a squared divided by h squared, the integral from 0 to h of z squared dz. So v equals pi a squared divided by h squared. The integral of z squared is z cubed divided by 3. And then if we substitute the values, the limits of the integral, then we would get pi a squared divided by h squared. We plug in first the top value, which was going to be h cubed divided by 3 minus 0. So that leaves us with the volume is equal to pi a squared divided by h squared times h cubed divided by 3. So these two cancel out 2 of these 3, and we are left with 1/3 pi a squared times h. So that is the volume of the cube. That is the volume of our cone.